the main goal of any Newton's second law problem is going to be to try to write the equation of motion, sometimes also just called the Newton's second law equation for the object. This is simply writing out the sum of the individual forces and then setting that equal to plus ma, minus ma, or 0. That is our equation of motion, and it analyzes the motion and allows you to solve for whatever the unknowns of the problem might be. So I love Newton's second law because unlike the kinematics where sometimes you have to hunt through and figure out which equation fits your situation if you're dealing with the constant acceleration equations, Newton's second law is just sum of individual forces equals mass times acceleration. And it's the same starting points. And if you learn to follow these steps that were outlined in the annotated worked example and in the list of the problem solving steps, then you know, every problem that requires Newton's second law, you will always be able to complete by working through these steps. The other thing about Newton's second law is that it doesn't go away in this class. We pretty much use Newton's second law from now, every week through the end of the semester. So definitely taking the time to become comfortable with these steps. So the annotated worked example has a very detailed two-body problem. You can see what happens. In that case, I'm going to work through the simplest case, which is, say, a 1D motion of a person in an elevator. So let's say we have a person and that they're standing in an elevator. And the elevator, let's say that the elevator, we don't care what way it's moving, we care what way it's accelerating now. So let's say it's headed up, but that it's slowing down. So in that case, we would have a downward acceleration. Let's talk about the equation of motion for the person. So let's write down our equation of motion for the person. You have to isolate your object. Step 1, free body diagram. Isolate your object. Here we care about the person, not the elevator. So I'm going to isolate my object. I draw everything as a box because I am a physicist and I can do that. And so when we don't care about rotation, we can just say, oh, it just acts as if all mass is at some center of mass, and we just then draw it like that. I choose to draw a box versus a point because then I can have multiple arrows and kind of keep the direction of ramps and stuff useful. So I do a box. There's my person. I can draw a smiley face on the box so it looks a little bit like a person. And so they're in contact with the elevator. There would be an upward normal force acting on them. That's the contact between the elevator floor and the person. That's also if they were standing on a scale, that would be what the scale would read because the scale would push up on them, they'd push down on the scale with that same amount. So the normal force up, and then we also are going to have the person's weight, mg, down. The force of gravity is the weight. We don't have anything happening in the horizontal direction, so I don't have to worry about it. So when I draw my axes, I can just draw vertical axes. And I generally choose positive y just to be up. I like my right-handed coordinate system where positive x is to the right and positive y is up. And so I just always work like that. You can choose positive y down, but then you have to be very consistent and clear. But what matters is that you do draw the axes near, but not on the diagram. Okay, and so the other thing that we have to do is decide what the acceleration is. And in this case, you can see the acceleration is down. So then I draw a big box around this, and this is step 1 of my process, drawing my free body diagram as was outlined in the previous videos. Great. Step 2, if we remember where we're headed with this, we have the Newton's second law, sum of forces equals ma. The left-hand side, sum of the individual forces. That's going to then be equal to the mass times the acceleration. So what I want to do is take step 2 is to just sum only the individual forces. I'm focusing on the left-hand side of Newton's second law. So step 2 is that now I write out the sum of forces, and in this case, I only have one dimension. So I'm going to do the sum of forces in y, and the sum of forces in y, I look at my diagram and I see that I have the normal force, which is up, So that's going to be equal to positive, because it's up, N. And then I also have the weight force, which is downward. And so that allows me to write minus, because the weight is down, so I choose a minus sign, times mg. So I basically taken the direction out of the vector by putting my plus and minus signs there, so that this n in this equation is a magnitude, and mg is also the magnitude of the weight. Remember, g is always positive 9.8 meters per second squared. It's the magnitude of the acceleration. It's downward, and that's why I have it written as minus mg. So that's step 2. I looked at my diagram and I saw how many forces I had acting in y. If I also had an x direction, and if you look right now and you take a second, go look at the annotated worked example. If you have an x direction and a y direction, you do step 2 in the x direction, and then you also do step 2 in the y direction. You separate your components. So take a look at that annotated example as I work through this one, and you can see how those steps play out and how they're similar even when you have a more complicated situation. All right, so now we move on to step 3. And step 3 now is I get to pick whether I'm going to set my sum of forces equal to plus ma, minus ma, or 0. And I do this by looking at the acceleration that I did in step 1. So step 1 had all the hard work done, and step 2 and 3 are just to put it together into equation 4. So I go to my original diagram, and I see that my acceleration is downwards in my negative y direction. So for step 3, I'm going to say that my sum of forces, so I say plus n minus mg, and now for step 3, I say that equals negative ma. And this is my equation of motion, where I chose negative ma because my acceleration arrow is downward, and I'm accelerating downward. And now that I have n minus mg equals negative ma, if the problem asked for what's the normal force on the person, I could solve for that. If it gave me the normal force and their mass and asked me for the acceleration, I could solve for that. The goal is to always get this equation of motion and box it. Then do that for every object you have. If you have 2 objects, you write an equation for each one. If you have 3 objects, you write an equation for each one. If I have an object, and again, look at the annotated worked example, where it's moving across a surface, I might have to do the sum of forces in the vertical direction. And that sum of forces in one direction will always be 0 because I have an axis that is perpendicular to my acceleration. So go ahead, look through that annotated worked example alongside this example here, as well as the list of steps. And let me know if you have any questions while you work through the problems.